So I'm going to be showcasing you how I was able to create my object detection model. This model is very, very important is because essentially this is the foundation for the drone detecting my face. I'm going to show you the tutorial using Google Colab. And one of the biggest reasons why I use Google Colab is because I get to have access, well, actually, I like to work on my laptop because I get to kind of like work on my data science projects on the go. But another great feature about it is I get to use a lot of the GPUs offered by Google. In this case, when you do NVIDIA SMI, which is short for System Management Interface, you see that I was using an A100, which was at the time the best GPU in the market. I think currently right now it's the H100. But you know, at the time it was the best GPU on the market that I could have used, and it had 40 gigabytes of RAM. My current setup right now I think is an RTX 270 with about 8 gigabytes of RAM. And just to give you some context, when I was running my model, training it, it took about 4 hours to complete, but when I used this A100, it took about 45 minutes. So it was pretty significant. And that's actually really important because taking 45 minutes basically means that I get to launch my product as fast as possible, as opposed to waiting 4 hours, right? Because at the end of the day, what's most important is really speed and velocity of how you can get a product going. The faster it is, meaning the faster you can launch it, means the more things that you can do as opposed to just having to constantly wait for things. Anyways, that philosophy aside, the tutorial will basically be done using Google Colab. I highly recommend Pro. You could still get away with not doing it, but I'd highly recommend it considering it's only $16 a month if you are able to afford it. I cannot say that. I cannot attest to it enough. So how do I begin? Well, first of all, we need to link Google Colab with Google Drive. And how we do that is we create a mount. And when I give it the directory of where it needs to go to, in this case, contact and drive, now we have a connection between Google Colab and Google Drive. Once that's done, I'm going to be asking you guys to install these libraries. The first one is AutoDistill. AutoDistill, in a sense, it's a model distillation. And it refers to the process of transferring knowledge from a larger model to a smaller one. And why that's important is because it makes the model more efficient while retaining the accuracy. Because one of the downsides having a very, very large model is that it's very, very slow. So if you're kind of able to get the best of both worlds, then that would be very, very fantastic. And one great thing about AutoDistill is it has a library called Caption Ontology, which is going to help me with the data labeling, which I'll show you in a few moments. Once you install that first library, the other two libraries I want you to install, there are two extensions for AutoDistill. One is Grounded SAM, which is short for Grounded Segment Anything Model, and this is used for the image segmentation and object detection. The other is YoloV8, and YoloV8 is just a fantastic model to include, is because it creates a real-time object detection model for detecting objects and images and videos very, very efficiently. The other two are going to help me, and these libraries, for instance, PyTorch, is going to help me with building and training neural networks, which I will need for my computer vision project, as this is a object detection project. RoboFlow, as it just gives me all the tools for data collection, annotation, training, and deployment, and it integrates very well with various machine learning libraries. And finally, but definitely not least, because you're going to see this a lot, is Supervision. This library is used to create and manage annotations for machine learning models. It can help me supervise and manage various processes related to data labeling or model training. So with that out of the way, the next thing I'm going to do is import OS. Why do I need to do that? Is because, well, I've linked the Google Colab with Google Drive, but I need to begin to go into the image folder. Why? Is because that's where I'm going to be applying my AutoDistill very, very soon. So I kind of create a new directory. I say go to content, go to drive, my drive, and images. And that's where images is right here. Yeah, my drive and images. I'm then going to change the directory to the new directory. And over here, I just basically print get CWD, which is get current working directory. And this is, again, just to confirm if this really did work. And I associate a variable to it, which is the image directory path. And again, I print it. Listen, it is a bit overkill, don't get me wrong. But you know what? Sometimes I feel like I get so lost that it's just better for me to have this stuff than to not have it at all. So you don't necessarily need to do it like this. I like to because it just gives me peace of mind. Yes, everything worked. So now I need to import Supervision. Why I need to do that is because I wanted to showcase to you how many images that I have. In this case, I have 677 images. I was able to do that within supervision. I then do list files with extension. And the directory is that image directory path that I had created. And in this case, the extensions are JPEG. So I was able to do an image count by just getting the length of that image path, and it was 677. Why that's very annoying is because I'll have to create bounding boxes for all this stuff. And in order for me to create that means I have to create 677 bounding boxes. And how that is, I have to kind of put a bounding box on the face, and then data label it face, and then rinse and repeat over and over again 677 times. I'm good, thank you. Especially considering that we have something like AutoDistill, which I think when you have to do with large object detection images for object detection, it should be the norm. So I say from AutoDistill detection, import that caption ontology. And this caption ontology, you're going to have two lines of code codes you'll have to write. One is going to be the prompt, which is the text description, and the second is going to be the class. So in this case, I say, look for the class that is face and attribute it the text description face. Okay, so that ontology part is done. Now I need to get ready to make the data set. So I make a new variable with this new directory, which is the my drive data set, and this is where you'll see it right here. So detect run data set. And I'm going to make that as my current directory. So kind of print it again just to see how it goes, and I'm going to now use that AutoDistill grounded SAM that I used that I imported right here. So now I have the grounded SAM, and now I'm going to be making the base model. So this code basically says is that it creates an instance of the grounded SAM using the specified ontology to guide the model's understanding of the objects it's detecting. So I kind of gave it the steps. I said, hey, the text description is going to be face and the classes are going to be faces. So when you are going to do the image segmentation object detection, know these rules beforehand. So I'm now creating the database, taking the base model, and I'm beginning the labeling process. So I said, you're going to take the images. So it's the input folder from the image directory path that I had created here, which all extensions are going to be JPEG, and you're going to then output it into the dataset directory. And this is where I'm going to be doing all my training. So I kind of call it my dataset directory path. And so once you run this program, it's then going to kind of go through all this, and it will complete. And finally, you'll get a dataset folder that you had created with all these folders within them. The most important ones that you should know are train, valid, and data.yaml. So over here, I get these files. So in this case, I'm kind of dealing with train. So in train folder, I have these two other folders, labels and images. And as you could suspect, it has the labels and the images of the images that I'd first uploaded into my Google Drive. And also a data YAML path. And what a YAML file is, it's especially in object detection, is that it contains the class labels to configure the training and evaluation of the object detection model. So it has the path of the annotation, the path of the images. It also has the classes. So when I have to put all this together, it's going to use data YAML as like a blueprint or a pipeline as to like what it's looking for, where to go. The next code after that is the dataset detection, is the detection dataset from YoloV8. And what this code is that it loads the dataset by reading the images and their corresponding annotations, in this case from YoloV8, and applying the class mapping. So putting all this together and configuring and then it prepares the dataset for object detection tasks for my training. And in this case, once I had done, so I basically say dataset, detection dataset from YoloV8, the image directory from the images, the annotation from the annotations, the YAML is where you're going to follow all this stuff. And once I ask for how many is in this dataset, it's 541. That means that not all my images got labeled, and that actually makes sense. In this case, if I go on runs and detect train 2, because I had run this twice actually. So let me go take a look where it is. I believe it's this one. In this case, you see, this was able to make a detection a bounding box on each and every face except this one. And the ones that don't get counted are obviously, well, they don't show up as a number. So in this case, it's far less. But I had so many that I was kind of willing to keep going because at the end of the day, I wanted to see what would happen anyways. And in this case, not much. So I was pretty happy with that. And as you can see, I then wanted to kind of see how does it do it? What is it doing? Is it to my liking and things like that? And honestly, I was pretty happy with it. I never put a bounding box. I never labeled this, and it seemed to identify them pretty well. Sometimes it would give me a little bit of a double. So in this case, this program, this model thought that it had seen two faces when in reality it was one. But overall, again, it was pretty good. I mean, even in the side of the face, it was still able to detect it, and it was able to even segment it very, very well. So once all that had done, now it was kind of begin to do training. And epochs essentially means how many times I need to go through it over and over again. How many iterations, essentially. In this case, I said 100 iterations. While this isn't always the case, the more iterations you do, the more accurate it can be. But that is not like, it doesn't continue to infinity. At some point, actually, it can hurt you more than it can help you. Because at the end of the day, right, you don't want the model to be so overfitting where it's not really, it's kind of just copying rather than really predicting. So I thought epochs 100 was enough. I think anything more than that was a little bit overkill. And when I was kind of like reviewing everything and I was seeing the box loss and things like that, and I saw that there was a lot of decrease, which I thought was good enough. And again, the best way for me to test it was to get it as quickly as possible so I could put it into my drone and see it, and I was pretty happy with it. So what are all these box losses that you see? Well, once you run the training for this, which by the way will be through this code, so you're going to import Ultralytics, import YOLO, and then include Ultralytics. Model equals to YOLO, model train that data YAML. Again, the YAML has the annotation, it has the training, it has the classes. Do it, and you're going to basically train this model 100 times. Okay, so now you're going to then get results once it's done. And you're going to get this, again, it might seem pretty like a lot of information, but really a lot of it makes sense. First of all, these two are essentially the same thing. The only difference is one is with training and one is with validation. And so the first one I kind of wanted to talk about was box loss. What box loss is that it measures the loss associated with predicting the bounding box coordinate during training. So at 1 basically means it was very, very bad. It was not doing that well. And over time, with much more epochs, and if actually at some point around like the 80 to 90 epochs, it got even better. It was pretty good. And now it's very good, right? It doesn't have as much losses. Maybe I could have, if I increased the number of epochs, it would have been done better. But honestly, I thought it was good for what it needed to be, especially considering I wanted to just kind of get this project going as fast as I can. So, and the same thing again. So it's train and it's validation. The next thing is classification loss. How is it able to classify the images? It's the loss associated to the object of the classification of these objects during training. More loss, higher the loss, meaning that not as accurate as it is, and the lower it is, the better it is. Now here's this one, DFL loss. DFL stands for distribution focal loss. And it's basically, you want to see, it's a loss, it's like a loss related to, it improves the localization precision during training. Long story short, it's like how predicted bounding boxes are distributed around the true object location. The better it is, the lower it shall be. And in this, actually, another really cool thing is this one. So metrics MAP 50. What that is that it shows how can I explain this? It measures the mean precision at 50% IOU threshold in terms of batch wise. So what is IOU? IOU stands for intersection of union. And as you can see in this case, it's not that good. It basically means the predicted and the actual one, it's just not that really good together. It's pretty poor. But as they get closer and closer, this is where it becomes really excellent, which in a way you basically can say a higher IOU indicates a better alignment between the predicted and the actual bounding boxes. Now going back to the results, you could see here that it got higher and higher. It got more towards that 90%, just like how here I showed it to you, which means that the predicted and the actual bounding boxes are getting closer and closer together. That's fantastic. And with that shows an increase in precision and an increase in recall. And what recall basically is that it indicates how many of the actual objects were detected correctly. So the higher it was, that means the more of the actual true images were predicted correctly. So once that's done, I wanted to then just like, I was like, okay, let's go test it on my drone ASAP. So how did I do that? The way I had done my model, which I'll show you in the next episode, I decided to format it into an Onyx file. And Onyx space allows you to, it's an intermediary machine learning framework. And the reason why I like to use it is because it allows me to convert between different machine learning frameworks, which you'll understand quickly in my next episode. But once I had done with my training, I had taken, and that training, by the way, it goes into detect, train to, weights best. That's where my custom trade model is, and I wanted to convert into Onyx. The next episode after that, I'll be showing you what I was able to do with that and how I was able to implement that into my drone to successfully create an autonomous drone. And I hope to see you guys in the next episode. Thank you, take care, goodbye.